The internet became a commodity, service available to a lot of people, especially in the Bay Area and some other metropolitan areas. As a result, people, especially those venture capitalists, saw the value in the internet and say, hey, we can do a lot of stuff and make a lot of money using the internet. So these venture capitalists started to fund, engineers, software engineers and developers, and say, okay, give me an idea. Oh, I think we can use the internet to do this, advertisement. I think we can use the internet to do this. We can host video content so people can watch TV from the internet. All great ideas and potentially can make a lot of money, right? Okay, so that's why year 1999 is probably the peak, and then 2000 was basically the transition, going back down again. But those years were called the boom years of the dot-com. Okay, and then what happened? Because of all these demands, all these venture capitalists pumping money into the Silicon Valley, all the well-qualified software engineers and programmers were absorbed just like that, gone. Okay, nobody with that kind of qualification is available anymore. They're all hired. So what do they do next?
They have to invest in schools to train the
They go to universities. Okay, so they go to San Jose State University. They go to Berkeley. They even go as far as UC Davis to try to recruit talents for developers, people who know how to write programs and can be trusted and kind of know what they're doing. I know about this because I was recruited. Okay, in the summer of year 2000, I was not, I have been out of UC Davis for a long time already, but because of some of the connections, I was recruited to this company called iScale. And I was only working, I only had to go to meetings every Thursday. Unfortunately, the meetings are always in Palo Alto at 7 p.m. So I have to start to drive at 4 p.m. here, and sometimes I can and sometimes I cannot make it to the Bay Area at 7 o'clock. So I will attend a 1 hour meeting over there. The meeting itself only lasts for 1 hour. And then there's usually an hour and a half dinner after that, and then I drive my way back to Sacramento. Okay? But 1 day a week, not too bad. Okay, if I had to do it every day, I would go insane. But if it's just 1 day a week, and I was making $4,000, just for that, so not bad. Okay, a lot of the graduate students at UC Davis also got recruited. Okay, so some of the graduate students actually put their graduate program on hold to work for this company. Okay, because guess what? The professor they were reporting to, the advisor, was also working for this company. So nobody was available to do any research or lead the people to do any research. So basically an entire lab at UC Davis just transplanted into the Bay Area. So they were all making good money in the Bay Area. Okay, so what happens when graduate students are all gone, used up, and you cannot find any more? You move on to, go ahead. Undergraduates, right? Undergraduate students. So they do, okay? And then what happens after the undergraduate students are all gone because they all have jobs in the Bay Area? High school students, right? And that's how far they have gone to try to recruit people to do programming. Now, I'm not saying high school students do not understand programming, they cannot get a job done and stuff like that, but they do lack the experience. Okay? They lack the experience, and they think they can program just by understanding some of the concepts and read some of the books in PHP programming, MySQL, and stuff like that, and be able to put things together. The answer is yes, they can put things together, but do they know how things work to the point where, oh, this is not secure? Okay, if you do it this way, people can do SQL injection and basically get the entire content of the database. No, they don't know that. But let me ask you another question. What if the code that they are copying and pasting from a book had a bug? Can these people analyze the program from the symptoms and go back and say, I think I know how to fix this? Nope. Okay, most of these people were able to copy and paste and change the code enough to make it work. But when there are problems, when there are bugs in the code, they would not be able to diagnose and find out, how to fix problems. Now, why is that important? Fixing things. Why would fixing things be important? Okay, go ahead.
That's what I was going to ask you. Where do you say your analysis experience comes from? What is that? Is that outside of computer science? Is that math?
It's experience, and also what you do when your program does not work. Okay, that's the question. Okay, and you raise your hand too. Go ahead.
I just wanted to say it's just years of practice, and that they need to go back and look at their program to figure it out, and it will lead into profits for people who do know how to do that kind of stuff.
Right. Exactly. Okay, so that's one thing that separates good programmers, developers, and software engineers from the ones who are not so good. Okay. I also, I was also a TA, a teaching assistant at UC Davis when I was over there as a graduate student. So, and like 1 or 2 days before the due date of a homework assignment, that was a C++ homework, C++ class. So 1 or 2 days before the due date of a homework assignment as a TA, I have to go to the computer lab and help out the students. So what I saw was kind of interesting. Okay, instead of using a debugger to debug their programs, they would use printfs. Okay, basically they were just spewing out all kinds of information from the program, hoping that they will catch the reason why the program is not working the way it is supposed to. And then what I saw was even more troubling, because in order to quote unquote fix the problems, some people will be so desperate to resort to throwing a dice. Okay. Now, how can you fix a program by throwing a dice? I can show you exactly how. They would look at a conditional statement or a sequence of assignment statements, and they would just do random changes. They would just try to change the ordering of 2 statements and see if that fixes the problem. They would change greater than to greater than or equal to, or the other way around, to see if that's going to fix the problem. Okay? Do you think making random changes like that will fix a problem?
Not very often.
It's kind of equivalent to a car mechanic. You're going into your car and go like, you know what? I'm gonna fix the problem by unhooking this this cable here and plug it over there. But the plug size doesn't even match. It's okay. Just have to make it hard. Do it harder, and it will fit. It will fit, right? It's the same thing as trying to fix a car. Remember those good old days where cars have a lot of vacuum tubes and stuff like that. It's like yanking all them out and re-plugging everything in a different order and see if that fixes the car. Okay, not likely to happen. In fact, it's more likely that something else will get broken because of that, right?
Make a backup.
Make
sure you make a backup.
Yeah, it's kind of hard to make a backup of a car engine, though.
Try.
All right. So that's why it is very important to approach debugging with an analytical mind. And this slide, or this entire topic, is about what is considered quote unquote analytical when it comes to looking at a program and trying to figure out what it is supposed to do. Is it going to do what it is supposed to do? That's the question. Now, I have to bring up these 2 giants in computer science. Both are considered the fathers of computer science, modern day computer science. Donald Knuth is still well and alive. He is still a professor at Stanford, and he has a particular view of computer science and what math should do in computer science. He's the one who kind of believes that because the tools are getting better, like Visual Basic or Visual Studio is very visual, it makes it possible for everyone to write programs. Okay, the barrier of getting into programming becomes a little bit lower. Okay. The other school, which is led by Professor Dijkstra, he passed away already, but he wrote a lot of books on computer science, and he actually invented a lot of algorithms that are still useful. He suggested that every programmer should be a mathematician first. In other words, before you can get your computer science degree, you have to get a math degree first. Okay? And that belief actually still exists, because in order to get a computer science degree, you have to take all the classes in calculus. In some school, you have to take linear algebra. In some school, you have to take abstract algebra. So you still have to take a lot of math classes before you can get your computer science degree. So there are these two kind of slightly different schools of thought, led by two giants in computer programming. What I think is, you have to understand math and logic, at least to the point where you can use it to debug your program. If your program doesn't work, you have to be able to have the tools to debug your program. But before even asking that question, how do you debug your program? How do you know your program is going to work or not going to work? You run it, okay? So you're using traces, right? You're basically tracing the program to see whether it is working correctly or not. Now, we are going back to the same question. How many test cases do you need to verify that your program is going to work for the next test case that you have not fed it yet? Okay? You can do a lot of test cases and it still may not catch the one case where it will break. Yep.
Don't you never stop running out of test cases because there's always something you can tweak here and there, or is it a finite number depending on the program?
Practically speaking, it is a very huge number of test cases because all computers are digital and we only have so much RAM in a computer. So technically speaking, there are only so many combinations that can happen with regular programs. With embedded programs, it is a different issue because with embedded programs like the one that that will run in your car or devices, even your cell phone has a certain portion of it that is not deterministic. Okay. Now, deterministic means when you run an algorithm, it's going to do exactly the same thing every single time, which is all the programs that we have done so far, all the traces we have done so far, they are completely deterministic. Every time I trace an algorithm with the same assumptions in the same variables, the program will execute in exactly the same way. That makes it kind of easy to debug a program because you change the program, you use the same test cases, then see whether it will do the right thing or not, right? But your cell phone has a lot of things that is not deterministic. Okay, what kind of stuff is not deterministic on your cell phone? When I press a button, okay, I just press the power button. That timing is undeterministic. The cell phone has absolutely no idea when I will press that button again, right? Now, when I press a button on my phone, it is actually interrupting some programs that are already running on the cell phone. So the interaction of the software that has to run when I press the button and the program that is already running on the cell phone before I press the button, the interaction of those things is no longer deterministic. And to test to make sure that the program is working all the time, regardless of when I press the power button, is an infeasible kind of thing. You cannot use test cases and traces to verify programs like that. Okay? All right. So we kind of have a general idea now that tracing a program is okay, it is important, but it is not by itself sufficient to show that a program is going to work all the time. Okay? So what we're going to do now is to kind of focus on what we call pre and post conditions, which is kind of corresponding to the pre line of a trace and the post line of a trace, except this time we are not tracing anymore. A precondition is basically saying what we know before the execution of a statement in a program. That's the precondition of a statement. Post condition is